Hello and welcome back to Chapter 1. Today we're going to look at Section 1.9, and that section deals with inverse functions. If you recall from Section 1.4, we could represent functions with a set of ordered pairs. So for example, if you had a function f of x equals x plus 4, and we're going from set A to set B, we can write this as f of x plus 4, and then do your set theory with 1, 5, and this 1 is coming from A, 5 is coming from B, 2 is coming from A, 6 is coming from B, and so on. So if you recall, I think back in Algebra 2 you guys talked about inverse functions, okay, and that's what this little f kind of raised to the -1 power is. This is an inverse function notation, and an inverse, if you reverse your x and y or interchange them, then we form an inverse function. So if you notice here, my original function had 1, 5 as an ordered pair. Down here in my inverse I have 5, 1. Likewise I had 2, 6 in f of x. Now in my inverse function I have 6, 2. And the pattern continues. And if you look at this, the domain in f of x, so the domain are x values, when you take the inverse, now becomes your y values. So the domain of your original function becomes the range of your inverse function. Likewise, the range or y values of your original function becomes the domain of your inverse function. And you can kind of see this now in this little diagram. The domain of your function and the range of your function are up here in this top part. Now, the range of your original function becomes your domain, and the range of the domain of your function becomes the range of your inverse function. And one other thing we want to look at with inverse functions before we start doing some examples is you have to make note that the original function and its inverse, they are essentially going to undo each other. Okay, so they'll undo each other. And if you do a composition, so if I do something like f of the inverse of f of x, this should give you the same answer as if you did the inverse of f of x, and these will both give you x if they are truly inverse functions. So let's look at that. F of the inverse of f of x. So what that means is we're going to do f of x minus 4, and this is right here's your inverse function. This is going to equal our original function, and f of x was equal to x plus 4. You just can't see that right now. So if I take x minus 4 and plug it in for this x here, we end up with x minus 4 plus 4. Our -4, +4, that's going to cancel and leave us with x. Okay, now if I go and I do this piece here, the inverse of f of x means I'm going to plug into my inverse function, I'm going to plug in x plus 4. So now I have x plus 4 minus 4. I see my plus and minus 4s are going to cancel, and I'm going to be left with x. So, because I could go f of the inverse of f of x and get x out, and then I could do the inverse of f of x and also get x out, that tells me that these two functions are inverse functions of one another. So example 1 says to find the inverse of f of x equals 8x. Then we're going to verify that both of them are inverses. So for f of x equals 8x, 8 and x are being attached. So to undo, attached by multiplying, so to undo that multiplying we have to divide. So this tells us that the inverse of f of x is equal to x divided by 8. And we'll go over how to do this later. So right now we just have to prove that these two functions, composite functions, equals x. So if I do the first one, f of the inverse of f of x means that I'm going to plug my inverse in, or go 8 times x divided by 8. And when I do that, my 8's are going to cancel, and I'm going to be left with x. Now I'm going to do the inverse of f of x. So I'm going to plug in 8x in for x into the inverse function. So that's going to give me 8x divided by 8, which again, my 8's are going to cancel, and we're going to be left with x. So because I have x here and x here, that tells me that my functions are inverses. Now the definition of an inverse function says that let f of g be two functions such that f of g of x equals x and g of f of x also equals x. Under these conditions, the function g is the inverse of f and is denoted by this little symbol here, and it's read f inverse. So f of f inverse of x equals x, and inverse of f of x equals x. Now we did talk about that the domain of f must equal the range of the inverse and vice versa. So the range of f must then also be equal to the domain of the inverse of f. Example 2 says to verify that f of x equals 5 divided by x minus 2 and g of x equals 5 divided by x plus 2 are inverses. So we're going to start out with going f of g of x. So I'm going to plug in g of x into every x. So I have 5 divided by x plus 2 minus 2. And when we simplify, our 2's are going to cancel. So then we're left with 5. And I'm going to rewrite this divided by 5 divided by x like that. And if you remember, dividing by a fraction is the same thing as multiplying by the reciprocal. And when I do that, I see that my 5's are going to cancel, and we're going to be left with x. Now likewise, over here I'm going to do g of f of x, and that's going to give me 5 divided by x minus 2 plus 2. So to simplify this piece here, I'm going to rewrite that. So this is going to give me 5 divided by x minus 2 plus 2. Dividing by a fraction is the same thing as multiplying. So this is really 5 times x minus 2 divided by 5. And then we're still adding 2. Your 5's are going to cancel. You're going to be left with x minus 2 plus 2. Your 2's are going to cancel. So again, we're left with x. Now when we go to graph these, you'll see that if you have a point AB that's on the graph of f, then when you invert these two, the point BA will lie on the inverse of f. And that's because the inverse of f is really a reflection of f over the line y equals x. So if you notice here, this gray line is our original function, and when we take the inverse of it, it's being reflected over this dashed line here, and it's now going to look like this black curve. And once again, you'll note that our original point AB now becomes BA. So example 3 says to graphically show that f of x equals 2x minus 3 and the inverse of f of x equals 1/2 times the quantity of x plus 3 are inverse functions. Now you can graph this and look at it, Or I'm just going to pick a few points and plug into my function. And if I pick the point -1, -5, 0, -3, and 2, 1. So these are going to be for my f function. If I plug those in, if I go 2 times a -1, and again I'm doing this up here, 2 times a -1 is a -2 minus 3 gives me this -5. So if I come over here and I plug in the point -5, -1, this also should be a solution. So if I go -5 plus 3 is going to give me a -2. And again, I'm doing this all right here. -2 times 1/2 is going to give me a -1, which is what I would expect here. And you can do this for each one of these coordinate points. And when you plug these in, you'll see that these actually are inverse functions. And with our inverse functions, we have what we call one-to-one functions. And this is where each value of the dependent variable, whether it be y or f of x, corresponds to exactly one value of the independent variable. So a function has an inverse if and only if, and that's what this IFF is, so if and only if, we have a one-to-one function. Now, like I think it was section 1.1 or 1.2 when we talked about functions, we have a little test to tell if we're going to have our function's going to have an inverse or not, because not every function has an inverse. And this is called the horizontal line test. And the horizontal line test says if a function will have an inverse if and only if no horizontal line intersects the graph of f more than once. So if we just do a little sketch here, and I take a linear line, and I come in here and I draw horizontal lines, there's nowhere on that function where my horizontal line is going to touch more than once. So that tells me that the equation of this blue line here has an inverse. Now let's look at another scenario. Let's look at a parabola. If I go in here and I draw a horizontal line, I see that I hit right here and here. So because I hit more than once with my horizontal line, that tells me that my squared function does not have an inverse. And the last thing we're going to look at today is we're going to figure out how to find an inverse algebraically. The first thing we're going to do is we're going to use a horizontal line test to determine whether we have an inverse or not. Because if our function can't have one, we're not going to waste our time trying to find one. Then we're going to replace our f of x value with y. We're then going to go in and swap or interchange our x and y values and then solve for y again. We're going to replace our y value with, and this here should be the inverse of f of x. And then we're going to verify that f and the inverse are inverses. So let's go ahead and do that in our next example. Our last example says to find the inverse of f of x. And f of x is equal to 5 minus 3x divided by 2. So if you graph this on your calculator, you'll see that we have a linear function. And that linear function is going to give us, it will pass the horizontal line test. So we can kind of say that step 1 checks. Now step 2 says to replace f of x with y. So now I have y equals 5 minus 3x divided by 2. Step 3 says to interchange x and y. So this is now going to give me x equals 5 minus 3y divided by 2. And now I have to solve for y again. So I'm going to multiply both sides by 2 to clear out this denominator. So that's going to give me 2x equals 5 minus 3y. I need to get rid of this 5. So that's going to give me 2x minus 5 equals a negative 3y. And then I need to get rid of that negative 3, so I'm going to divide everything by a negative 3. And when I do that, I end up with a negative 2/3 x plus 5/3 equals y. And then my last thing is I'm going to replace the y with my inverse of f of x and say the inverse is equal to a negative 2/3 x plus 5/3. You can double check it. And that just completed section 1.9. Have a great day.